Thank you. I would have loved to say that Errol saved the best for last, but unfortunately it's the other way around. It's the worst for last. So my name is Toghrul Marramov. I do research at Scroll, and today I'm going to talk about zero-knowledge proofs in the world of rollups. So unless you live under a rock, you probably heard about rollups in one way or another. You've probably seen this tweet by Vitalik referencing his article, the famous article called Endgame, which explains the rollup-centric future of Ethereum. Or you might have seen this GitHub repository by Barry Whitehat, which was the first one to mention rollups as a term. Or you might have seen this ETH research article by Vitalik, which mentions rollups and coins the term zero-knowledge rollups. Or you might have seen this article by John Adler, which for the first time introduces optimistic rollups. Or you might have seen me complaining about rollups on Twitter. So before we define what a rollup is, let's first define what an L2 is. And for that, I'm going to reference the good old folk L2 bead. So they define L2 as a chain that fully or partially derives its security from an L1 Ethereum, so that users do not have to rely on the honesty of L2 validators for the security of their funds. And you might think, what is an example of an L2? So the main one that was there before the rollups were around, that you probably heard of, is Lightning Network, Bitcoin's Lightning Network, which is a payment network. Another one are optimistic chains and Validiums. So an example would be Metas or Immutable X. But bear in mind, as I note here, not every researcher considers optimistic chains and Validiums to be L2s. There are nuances there, I'm not going to go into it, it's boring. And of course, the main subject today, rollups. Optimism, Starknet, Arbitrum, there are too many to name. So with all the waffle out of the way, let's talk about rollups. So what is a rollup? So we define a rollup as a protocol that inherits the following guarantees from the underlying base layer. And by base layer, I mean a layer with which the rollup is interconnected. So let's say if you deploy a rollup on Ethereum, Ethereum would be considered a base layer for a rollup. So the first, and probably the thing that differentiates rollups from other L2s is data availability. What is data availability? Data availability guarantees that the user can access the data from the protocol for some predetermined amount of time, say a year. So in case of a rollup, that would be the transaction data that was batched on an L1. The second guarantee is ordering. What is ordering? So if you submit a set of transactions on chain, it has a specific sequence. And once that chain is finalized and it's part of the canonical chain, that sequence of transactions, it guarantees that they can't be reordered. So let's say you can't replace transaction A with transaction B or just mix them around. And the third property is censorship resistance. It might be quite straightforward to define censorship resistant, but if you go into the details, it's actually quite difficult to do. But for the sake of brevity, let's assume that censorship resistant guarantees is when you can, when the protocol can add your transaction into the canonical chain within a predetermined amount of time, let's say a week, assuming that you're paying enough for the transaction. And then the most important one for this talk, state transition correctness. So what's state transition correctness? A state transition is a procedure where you take a system, a state of the system. So let's say, I don't know, let's say you have a state that Alice has 10 ETH and Bob has 0 ETH. You apply some input data and you get an output, which is the resulting state of the execution based on that input. So for this example, let's say the input is a transaction that says, send 5 ETH to Bob from Alice. And basically, the state transition is the procedure of applying that transaction to the state. And the resulting state is Alice has 5 ETH and Bob has the other 5 ETH. And why it's so important is because if you can ensure that the state transition is done correctly, there are no trust assumptions remaining. So basically, you can just, as long as you assume that the system used to prove the correctness is correct, you don't have to rely on anything else for the for the correctness of the bridging. And the way you ensure the state correctness is how we differentiate between two rollup flavors. So the first rollup flavor is an optimistic rollup. An optimistic rollup ensures that basically implicitly assumes that the state is valid unless somebody challenges it. So how it works is, let's say I'm a sequencer, I submit a batch of transactions with a state commitment, and Errol, for example, here sees one of the transactions. He's like, no, the resulting state is incorrect. So he initiates the challenge. And if the challenge is initiated within the dispute period, the standard period is 7 days. We go back and forth until he either proves that I'm wrong or I prove that his challenge was faulty. And basically, you can class this as innocent until proven guilty. And then the second type of a rollup is called a realistic. No, I'm joking. It's called a zero knowledge rollup. Yeah, I know. We're 7 minutes in, and it's the first time I'm mentioning zero knowledge at a conference about zero knowledge proofs. So, or as the good folks at Starkware like to call it, validity rollups. But I'm not going to do that. Sorry, Eli. It's just wrong. So, what are zero knowledge rollups? Zero knowledge rollups are a system that is based on a principle of guilty until proven innocent. So as long as the system doesn't accept anything until you prove that it's correct. So, and how is it relevant to zero knowledge proofs, you might rightly ask. So Starks and Snarks, the zero knowledge proof systems, have one important property that we use in rollups. It's called succinctness. So what is succinctness? Succinctness is when the size of the proof is small relative to the statement being proven, and the proof can be verified quickly. So in essence, despite what the name suggests, rollups are not privacy preserving. So all your data is still there, and you can see who's sending money to whom, etc., etc. But we use the zero knowledge proofs because they're succinct, so they're easy to verify on chain and cheap relatively. I mean, compared to just replaying the transaction. So, as I said before, zero knowledge proofs, or we refer to them as validity proofs because users might get confused if they hear zero knowledge proofs in this context and think that it's privacy preserving. So, are utilized to prove the correctness of the state transition. So how it works is, let's take an Ethereum as an example. Ethereum executes a block. It produces the resulting state. So you take the execution trace from Ethereum, put it inside the prover, produce the validity proof, and then the user, instead of re-executing all the transactions, can just apply the end state and the state diffs, and he'll get the same result, which is faster and cheaper. So what's the advantage of using validity proof versus the optimistic system? It has fast finality. As soon as you submit the validity proof, you don't have to wait for challenges or anything. It's final and that's it. The other thing that we don't have in validity proofs is there's no one-of-n assumption. So for safety, so in optimistic rollups, we're always assumed that there's at least one honest user running an L2 node that is capable of challenging and disputing the state commitment. And here, as long as the zero knowledge proof system is correct and the circuit implemented is bug-free, you don't have to trust anyone. And then probably currently the most important benefit of using validity proofs is that they can compress the data significantly relative to optimistic rollups. So in Ethereum, the data availability costs a lot. So the difference between publishing, say, I don't know, 150 bytes per transaction versus publishing 10 bytes of transaction per transaction is significant. So for example, DYDX has publishes around 7 bytes per transaction, whereas an optimistic system like Optimism publishes around 130 bytes per transaction. So the difference is quite significant. And that's the main cost associated with the rollups. So what does Scroll do? What we're building is a zkVM-based zero-knowledge rollup. Now you might have heard about zkVM in the past 2 weeks. It has been making rounds on Twitter. So what is a ZK EVM, and specifically what is our ZK EVM? So our ZKM is a joint work between us and Ethereum Foundation's privacy scaling explorations team. And what we're building is what I call a specification compatible circuitized EVM. What that means is that the implementation of the circuit that we use is following the Ethereum yellow paper. So you can just extract the execution trace from Geth, put it in the prover with the circuit, and you get the validity proof. You don't need to modify anything or implement the clients, etc., etc. And that allows us to have a minimum additional attack surface versus pre-implementing everything from scratch and also transpiling or interpreting like other ZKM approaches do. And basically, we're also 100% compatible with all the existing Ethereum tooling. So what is our current status? We are open source, so you are more than welcome to check our GitHub and all the repositories that are out there. We're always going to be open source, so you can fork it and do whatever you want with the code. We just announced our pre-alpha testnet launch last week in Paris. What an pre-alpha testnet is for us is a minimum viable product. So the circuit doesn't really support all the opcodes right now. So what we did is we made a private fork of Ethereum. We forked a few popular dApps, so Uniswap, for example, and we deployed them on top of our testnet. What users can do, they can sign up, and then basically, if they are whitelisted, they can go and play with our testnet and see that the user experience is not much different from using the actual Ethereum. And we have the public testnet coming later this year, sure. And the public testnet will be completely permissionless, so you are free to deploy any of your contracts or use it however you like. There's no limit set on anything you can do with it. That's basically it. Thank you. Any questions?
Any questions in the audience or talk first from anybody?
Thanks for the speech, Toghrul. How are you and how are ZK rollups in general planning to do censorship resistance, and is scroll the same as everyone else, or do you have a different approach?
So there are multiple approaches there you can take as a rollup to tackle censorship resistance. People at Starkware even have an argument that you don't need to inherit the censorship resistance from day one. But my argument is that if you don't inherit the censorship resistance, you're not really a rollup because you need an honesty assumption for that. So how we do it is similar to how Optimism works in a sense, and Arbitrum. So you have an inbox on an L1 bridge, and you submit your transaction there. And that transaction has a deadline, let's say 24 hours. So if the sequencer doesn't include it in a batch within 24 hours, no batches are accepted without that transaction being included into it. So essentially, the sequencer has two options at this point. Either stop producing and basically the liveliness guarantee of the rollup breaking, but it's not a problem if the sequencer is decentralized, or he or she are forced to include the transaction in the next batch.
If I understood correctly, that's just for the bridge, is that right?
Sorry?
Is that just for the bridge? I heard you mentioned the L1 transaction. I was wondering on the L2 level, like.
It's both the bridge and the L2 transaction. You can just submit it through an L1. So the L1 doesn't execute the transaction. It just stores the data and the hash of it in the contract, and then it has a timer on it. So if it's not included into an L2 batch within a certain period of time, it doesn't accept any more batches unless that hash is withdrawn from the inbox and included into the batch.
Okay, thank you.
What's the technical blockers in terms of implementing a CKE? And you mentioned you were definitely pre-alpha, there's certain obstacles that are being implemented. What are the remaining ones?
So the main obstacles are two. One is EVM is not really zero knowledge friendly. So a lot of things introduce overhead. So for example, EVM uses CatCheck, and CatCheck is quite complex to prove in a circuit. And the other blocker, it's not really a blocker, it's just probably the biggest difficulty for every L2 out there is that paradoxically decentralizing L2s is much harder than decentralizing an L1 because you're already paying for an L1 consensus essentially for all the services. So there's no reason to introduce an additional consensus because that just introduces unnecessary overhead. So you need to strike a balance between minimizing the overhead and also being decentralized, and that's been quite a challenge until now, until basically for all of us working on L2s.
Any more questions for Tog? Okay, thank you very much again, Toghrul.
Thank you.